Alright, throughout this lesson we're going to look at examples based on both exponential and logistic growth. We're going to start with some simple exponential models. In the short term, we can handle population growth as an exponential model. Notice it says in the short term. And then if we have this rate proportional to the population, we can write a differential equation of the form dp dt equals kp, where k is the relative growth rate of the population. And in this video, we're going to look at the first two examples where we're looking at short-term population growth and the development of models for that. So in example 1, we're told the relative growth rate of the population of Brockton is 0.031 and its current population is 56,800. Our first task is to write a differential equation for this population. In order to do that, this is very simple. All we need to do is take the relative growth rate and substitute it into the differential model. So the change in population with respect to time is going to be 0.031 times p. Alright, now in part B we're going to find a formula for p in terms of t. In order to do that, we're going to use two things. We're going to use the differential equation that we just found and the initial population. So we'll take the differential equation that we just found and we will integrate it via separation of variables. So I'm going to divide both sides by p and multiply both sides by dt. And then I'm going to integrate this. This turns into the natural log of the absolute value of p is equal to 0.031 t. Now population here for all reality is going to be positive, so I'm going to drop those absolute value signs and this turns into the natural log of p equals 0.031 t. I'm going to raise both sides e to that power. Oops, I forgot something very important like my constant of integration. We're going to raise both sides e to that power, and that gives us p equals e to the 0.031 t plus c. And now, using rules for exponentials, I can bring that constant out in front. It's a different constant now, but a constant nonetheless. And now I have my model almost finished, except I want to use the initial population to determine the value of c. And something you'll notice in all of these is that the initial population ends up being the value of c in every case. And so our formula for population in terms of t is population is equal to 56,800 times e to the 0.031 t. And if you're really paying attention, you'll find that instead of having to go through the process of separating every time, we can take the information that we're given in the initial example and just go ahead right to a formula for p in terms of t. And that's what I'm going to do here in example 2. The current population of Boomtown is p of 0 equals 93,000 and the relative growth rate is 8.7%. So my model is going to be population is equal to initial population times e to the relative growth rate t. And now we're asked in this example what the population is going to be after 7 years. And so I'm just going to go ahead and substitute 7 in here for t. And go ahead and calculate. And so we've got 93,000 times e to the 0.087 times 7. We end up with a population of approximately 170,989. number was it? 170,989. Alright, that's the end of this video. We'll come back and continue the lesson in the next video. See you then.